All right, so were there any questions? Did y'all work through those problems? No, I'm going to wait till the weekend. I'm just do it all on the weekend. Okay, you did them? All right. So hopefully you all had an opportunity to practice with those. And there aren't any questions. Well, good. Thank you for being honest.
Would you recommend though, like when you always have a fraction and you do like the new integral sign, just automatically pull it out? That's how
if it's a constant, yeah, you're just gonna just keep pulling that thing out. Yeah, because that just keeps your integrand a lot cleaner. You just got to keep track of all the signs and everything. All right, so we're going to proceed. We have an exam a week from today, right? Your first exam? I believe so. I didn't. I'm a slacker. Well, you know, my daughter was sick. I'm trying to catch a skunk. Oh, actually, I'll tell you what happened. If you really want to know, I'll show you. One of our faculty members sent out this problem. Sometimes we just send each other problems that are just kind of like, hey, look at this. You know, this is kind of interesting. And if you're bored, then do this. And so this was the problem that was sent out, was to solve this absolute value equation. So solve for x, and it's not that hard to do. You can just work through and do. Do you remember how to solve an absolute value? Like absolute value of x equals 4. You set up two equations, x is 4 and x is negative 4. It's the same thing here. Like you have the absolute value of something equals 3. So you first get rid of this outside absolute value, and you say this is equal to 3, and then you do it again, but equal to negative 3. And then you move things around, and then do it again with the next absolute value. And you'll have 2 more to look at, and then 2 more for this. And then each one of those, you do it again, and then you'll have 2 more and 2 more. So it's like 8 different equations or something like that. Anyway, it's pretty easy to solve. You get these are the solutions, right? So it's just an exercise. But then I said, well, what if x can be a complex number? So what if x can be like have an imaginary part to it? So that's a totally different ball game. And I asked that question, and then I went about trying to figure it out. So I spent all of yesterday, and I finally got it about 1 a.m. So that's why I didn't grade your quizzes. I was trying to do a math problem. All right? It was fun. It was real fun. All right. Where do we leave off? D. All right, here we go. So this is the example where I say rabbit out of a hat. And really, yeah, there's nothing like this problem. I mean, this is a very unique problem. You're going to see when we get it done, all right? It's not that it's super hard. It's just something's going to happen that's going to be like, okay, I didn't know we could even do that. First, I want you to notice that when you have the formula for integration by parts, I said the main thing is to remember it's like a transferring of the derivative, right? You're going to look at 2 different things. One of them is going to get differentiated. The other one's going to get integrated, right? And you get to choose. Now, on some of your homework problems, I know we just talked about Nolan, right? What was it, x squared plus 2x or something like that, and then cosine x? And you had to use integration by parts twice. The idea was that the first integration by parts reduces from quadratic to linear, and the second time through it took that linear down to a constant, and that was good. And then integrating this was fine because it just cycled between the sine and cosine. So we can kind of hopefully see now by looking at this that this is doable with integration by parts, because one gets better as we go. Now look at this one up here. If you look at the e to the 2x, right? If you choose that to be u, that when as you do derivatives, right, what's going to happen? Well, derivative of e to the 2x is itself, and then you'll have a constant in there. You'll have a 2 in there also, but it's not going to like get any nicer, is it? Like this one got nicer? And then when you integrate this one, then it's going to cycle back and forth, right? So are you ready seeing the trouble here? Like, you're never going to get one of these to get better. This is just going to go back and forth between sine and cosine. This one's always just going to be e to the 2x, e to the 2x. So it appears from first glance that this technique will not work on this because nothing's going to get nicer, right? Do you see that? Okay. But it's going to work. So let's see how. So the first thing I'm going to do is set up my table. I'm going to choose a u, and I'm going to choose a dv. And really, you have kind of a coin flip here of how you want to do this. You can choose your u to be the e to the 2x, and then your dv would be the cosine x dx, or you could go the other way. You could let your u be cosine x, and then your dv be the e to the 2x dx, right? Two options, really? So let's go with the first option, which was to let this one be the u, right? And this one's going to be the dv. That's going to be dv, that's going to be u. And let's just see what happens. I thought we'd go around the room today, and I would call on people. And I'd ask them to give me the parts of this, all right? So we'll start right here. And I don't know you real well yet, because I know these guys already. So what was your name? Carmelo. Oh, yeah, that's right. Okay, Carmelo. So if you have your name tag out there, your little name thing, I might. Do you have it? Yeah. Go get it out. Sorry. I was thinking about today, I'm going to have a quiz. Whoever has their name thing gets 100. Anyone who doesn't get a 0. I thought about doing that. You haven't done that yet? I can still do it? You can still do it now. Just get a piece of paper then, Matt. Just so you're fair.
That's our quiz for today.
No, I thought about that. I don't know. I said, you know what, I'll give him one more warning.
You can do it later on.
One more warning. Okay, Carmelo, you get to choose. You want to give me du or v? Okay, what's v? Sine or negative? Negative sign? Sine? Sine x? Okay. We move on. We'll go with Kirsten. Because you said, I thought you just said call on me a second ago.
What?
No? You were saying, oh, you were saying give you the quiz grade of 100. That's what you wanted.
Yeah.
Oh, but I'll call on you anyway. What's the derivative of e to the 2x?
E to the 2x.
Okay. And? Times 2. And then what do you always have to put right here?
Dx.
Dx. Okay, good. All right, so that's our table. Everyone agree? All right, so now what I'm going to do, let's see, we'll move on. See, Michael? Yeah? I'm going to put this equals, and then do you remember the formula yet, Michael? Like, in terms of u and v, do you remember what the formula is? Okay, so it'll be, so u times v. Perfect. Okay, that's it right there. So I'm going to go u times v. So this times this, e to the 2x times sine x minus the integral of, now let's move on to my back table there. Joel? Or Joel? Joel? I'm not going to call on you, Joel, because you have your name. Okay. So, what do you got? Yes, sir? What's your name? That's right. See, but I have to have visual for it to start to stick. Yeah, I'm going to make you go get a tattoo. What I was going to ask you is what goes in the integral? And you know what? If you're not comfortable with it and you're like, you know what, I don't know, just say I don't know. I mean, it's okay to do that. I was in a Cal 3 class the other day and I had a student, I was like asking him, he's like fumbling around through stuff and like we're all waiting. And I said, it's okay to just say I don't know. That's all right. You don't want to be I don't know when you're taking the test, right? Yeah. Okay. It's okay? All right, we'll move on. Yes?
Sine x.
Okay, so you're just going to do this one times this one. So it's v times du. So what would you like for me to do with that 2? Because it's a constant. You want me to pull that out now? Okay. I prefer to pull the constants out. Now that we're in the second day of this, hopefully after homework you've seen. All right, that's where we are, right? And from all appearances, we've done something, but it hasn't really gotten any better, has it? I mean, we went from an integral that had e to the 2x times cosine x dx, and now our new integral is e to the 2x, but now sine x instead of cosine x. So it really hasn't really done much for us, right? Okay. So you might be thinking, all right, well, maybe we should just quit. Let's go and do the same thing. Let's do integration by parts again. Let's use the same u. Let's use e to the 2x again. So I'm going to make a new table over here because there are some things that are slightly different in this new table. So I'm doing a second integration by parts. Do you all see that? So u is going to be e to the 2x dv. Kyle, what do you got for dv, Kyle? Actually, Kyle, I'm going to call on, what's your name? Miranda, do you have your name thing? No. You don't? Okay, so that's why I'm calling on you. Do you still have it?
Yeah.
You do? Okay, bring it next time, please. All right, Miranda, do you know what we're going to use for dv here? Sine x. One more piece. Sine x. dx, yes. Anytime you're working with this line, you're going to have dx's on that line, all right? And then, Alexis or Tony, who wants to volunteer? I'm looking for du and v. Okay, so what is it? Same as last time? I'm going to put the 2 in front. Is that all right? Alexis, he made it. He gave you, I guess, the harder part. So v? Negative cosine x. There we go. Look at that. We got all the way around the room. Okay, so what we're going to do now is we're going to rewrite the integral, right, using the ultraviolet minus voodoo again. But remember, my entire universe of what I'm looking at right now is this piece, right? So whatever I get with the formula, remember I'm going to have a negative 2 sitting in front of all of it, right? So what I'd like to do is I'd like to rewrite the entire line. I'm going to erase this because I don't have room for it. Can I? Feel okay with it? All right. So my next line is going to read this. Equals e to the 2x sine x minus 2, and then times whatever I get, right? So I'm going to put it all in big brackets. Here we go. All right, ultraviolet minus voodoo. So what would the ultraviolet be? So it was e to the 2x times negative cosine, right? So I'm going to write it this way. Negative e to the 2x cosine x. Everyone see that? That's ultraviolet from your table. Minus, no? Where the negative, go back to your table. Right, it was negative cosine here. All right, so minus integral, and then this times the one down here, right? So there's a negative and a 2. I'm going to take that negative 2 out. Right? Maybe I should go a little slower. I'm going to put it in here. Negative 2 e to the 2x, and then what's here? Cosine x dx. Any questions on what I did there? Yes? I'm good? All right, so I'm going to rewrite this. I'm going to put it right here. And you know what? I want you to do this also. On your next line, I want you to write down the original problem, which was this. This is what we were trying to figure out, right? This is what we're trying to figure out. We're saying that that's equal to this right here, which is e to the 2x sine x minus 2 bracket negative e to the 2x cosine x. And then here, when we pull the negative 2 out, it would become plus 2, right? So we get plus 2 integral e to the 2x cosine x dx, close the bracket. Any questions? Does anybody see something? The integral we're trying to solve for, right, has appeared again on the other side of the equation. And that might initially seem like a bad thing, but it's actually a great thing, as you're going to see on the next step. So what I'm going to do right now is that -2 in the bracket, I'm going to go ahead and pass it through. All right, so let's pass that -2 through. I'm going to rewrite the left side again. While I'm rewriting everything and distributing a -2 through, can you remind me, whenever you have an equation, what are the things that you can do when you have an equation? You can always do what on both sides? You can always add the same thing on both sides or subtract the same things on both sides. You can always multiply both sides by the same thing, right? Those are the types of things I can do. So I've removed the brackets by distributing a -2 through. Did I do that right? Yes? So I'm allowed to, at this point, look at this equation and I can add or subtract or multiply or divide anything on both sides. Except I can't multiply both sides by 0. That's illegal. So watch what I'm going to do. I have no idea what this is, right? That's what I'm trying to figure out. But I know I'm supposed to have -4 of these. So I'm going to add 4 of them to this side. And I'm going to add 4 of them to this side. And this is like adding apples to apples. If you add 4 apples, right, to what? This is 1 apple. You have 5 of them. Understand that? So what we get is, how many of these integrals? 5, you said? 5 of these integrals is equal to e to the 2x sine x. This went away over here, didn't it? And then we have plus 2e to the 2x cosine x. And that's all I have, right? That's it? And now I would like this to be just the integral, not with a 5. So why don't I just divide everything by 5, both sides of the equation? Is that okay? So I'm just going to have one of these is equal to this divided by 5. So I'm going to write 1/5 e to the 2x sine x. This divided by 5 plus 2/5 e to the 2x cosine x. And somehow, amazingly, we have integrated. We have actually found the antiderivative. Because look, we're saying the antiderivative of this is this, right? Now the only thing I'm missing here is the plus c. And that's because when you do it this way, when you have a problem that works this way, you never actually took an antiderivative, did you? Like you did it in your ultraviolet minus voodoo, the table, but other than that, like you never got an integral at the end that you finally integrated. It moved to the other side. So you never had that plus c pop out. So you just have to remember that all antiderivatives have to have some constant added. Do you see why I would call it kind of like the rabbit out of the hat? Because you never really, like it appeared again, then you brought it over. So it's just weird, right? Should we check it? No, you don't want to check it? Why am I the only one who's eager to check these things? It works. We'll believe it works.
So you just stop when you get the same one?
You stop when you get the integral that you were looking for in terms of something that doesn't have an integral anymore. See, there's no more integrals over here. When you do the first step of integration by parts, your integral becomes ultraviolet minus integral voodoo, right? You have an integral still to work with. But we've somehow manipulated it to the point where the integral we're looking for is equal to something that no longer needs integration. So what you see, whenever you see this sort of combination where you've got a function that's never going to get better or it's going to cycle, then you kind of got to hope that it's going to reappear on the other side. All right, let's look at E. Now, I already gave you the hint, which is, I wish I wouldn't have put that up there, of what you're supposed to do. But let's just make sure we understand that we can't really do anything else first. That's just not E. This is not just like e to the root x, right? Antiderivative of e to something is itself. I mean, it is, but if this is a function of x, then that won't work, right? Because if you take derivative of that, it's itself, but then times derivative of what's up there, but that's not over there, is it? So, no go here. So you start thinking maybe integration by parts. But if you're going to do integration by parts, what are you going to choose for u? What are you going to choose for dv? Let's see.
dv is going to be dx.
You want to try dv is dx? And then this would be the whole thing up here? Yeah? We could do that? We could try this. Y'all want to try it?
What can be the other way?
Well, let's just try it. Let's see what happens. Okay. This is right. And then coming down here, it's a little more complicated. This will be itself times derivative of what's up there. Like that, right? So derivative square root of x is 1 over 2 root x. Any questions on that? Okay, so let's do ultraviolet minus voodoo. Ultraviolet, x e to the root x minus integral voodoo is x times e to the root x times 1 over 2 root x, like that, dx. Do you agree? What else could we do with that? Is there a constant that we can pull out?
1/2.
1/2? Everyone see 2 down there? We can pull a constant out. I'll write e to the root x here. We have this x, right? And then we're dividing it by root x. What's x divided by root x?
X to the 1/2.
Which is just root x, right?
Oh, sure.
Is that right? Understand that? So we had this original integral. And when we did an integration by parts, we got this and then a new integral, right? And look at this new integral. I think it actually looks more complicated than the first one, doesn't it? It's not only e to the root x, it now has a root x in it. And you might be thinking, okay, u sub, I can just do u sub. Let that be u. There's a derivative of it. No, that's not the derivative of it, right? 1 over 2 times this is a derivative. So this is going to make a basic u substitution. And it's not a very natural u substitution. By the way, that could be done. You could keep going, and it's just ugly, but it could be done. I'm going to make a u substitution to start the problem. It's not going to look very natural, but just watch how great things are going to become. I'm going to make this substitution. Now, I told you when you're doing basic u substitution, you're always supposed to be looking for something in its derivative, right? Right? But in this problem, if I'm letting u be root x, I don't see its derivative here. But there was one example I did show you where we made a substitution even though we didn't see its derivative, and it worked. So there's not like, when you make a u substitution, it doesn't always have to be that its derivative is there. If it is, then great. If it's not, then who knows? It might work, it might not. I know that's not what you want to hear, but it's just the reality of this material. So I'm going to make this substitution. The derivative of this is, let's go back around the tables. Josh, I know you know the derivative of this. I know everyone on this table knows the derivative of this, so I'm not going to ask you. So we'll move on. Lewis, derivative? 1/2, yep. 1/2. Where, you want the root on the bottom, right? Is that the way? And then dx, right? Agreed? And then if I try and make this substitution, I know that I can replace this right here with what? U. And then I have to replace dx. And I used to play a matching game, didn't I? I tried to match these things up on both sides. The problem is I can't match because this doesn't appear there, right? But I'm gonna try and isolate dx. I'm gonna get this dx by itself. So if I'm gonna get dx by itself, what do I have to multiply both sides by? 2 root x. So if I do that, I can replace dx up there in the problem, right? I can replace the dx with this. Jared, what do you think is wrong with that? I mean, not wrong, but what sort of trouble do you think I'm going to get in if I replace this root with u and the dx with this? Do you see what the problem is there, Jared? I'll write it out for you real quick. Is that? I'm going to have two variables in here, right? I'm going to have x and du mixed together. And I told you that the whole idea of rewriting the integral is to be able to get rid of the x and turn it into u, right? But that's not going to be a problem because what is root x? U. It's u. And so we got lucky. That root x is u. And so this actually becomes 2u du is dx. Right? And so really now when we rewrite this integral, we've got e to the u, that's this. And then dx is replaced with what? 2 du, or 2u du. I can pull the 2 out. I can move the u to the front. And now that's where I am, right? And then you look at that integral and you go, well, did that get any better? So let's go around. We'll open it up to this side of the room. Anybody over here? Tell me if you feel like you can do this, like if you can attack this, how would you attack it? That side of the room only. Just to forget everything else here exists. All right? It's a brand new problem right there. There it is. I'll just put it in the corner here so we don't forget. We did make a substitution that u is root x. But ignore that if that's the new problem. Any ideas? Integration by parts. Why? That's right. Okay, so you have a polynomial. This is like x sitting in front of e to the 2x. And so you know if you use integration by parts, this, when you take the derivative, it'll drop down to a constant. Right? When you integrate this, it'll be itself. This is exactly like which problem? Well, it's not really up there, but it's kind of like A, isn't it? Where we had an x in front of sine. This is like an x in front of sine. This is going to switch back, right? I mean, it's not going to switch between sine and cosine, but it's not going to go away. Sine didn't go away either, but this one went down. Did y'all see that, everyone? So I'm going to do integration by parts on this. Good. If I do that, now watch what's going to happen when we do that. I'm supposed to choose what and what? U and dv. Uh-oh. I'm already using u. I can't use U again, because then you would represent two different things in the problem, right? Now I can use V, can't I? Because I haven't used V. So I can still choose a dV here. That still makes perfect sense. But I can't use U, so we'll use... Can't use X. X is already used. Z, K, right? Usually we'll use W. Now here's the thing. We like U, V, W. It's kind of like grouped together. Kind of like X, Y, Z. We like to use X, Y, Z together. We like U, V, W. Sometimes we like R, S, T. Those variables. So like if you're going to use S, then use R and T with it. This is just common stuff you'll see in mathematics. U, V, W. So I'm going to go to W now. I'm going to make a W substitution. So we can no longer use the cute little ultraviolet minus voodoo anymore, can we? So it's ultraviolet. I mean, it wouldn't make any sense. So it's more important for you to understand the formula, right? How to work with the table. This integral will become these two multiplied, right? Minus the integral of these two multiplied. What are we going to choose for W? U? For dV? E to the 2u du. All right, let's go. Where were we? Jared, I called on you. Let's see. We've done that table. James just answered, so it's... You volunteering?
Well,
Or you have a question?
Where did that 2 come from?
Yeah, I was wondering that
To
too.
you.
Yeah, I think that's.
Yeah.
Good.
It was in there. Remember we had that... We made the substitution u was root x. Du was 1 over 2 root x dx, right? And when I solve for dx, I multiplied both sides by 2 root x du equals dx, right? Do you remember that was 2 root x, and then I replaced root x with u? Okay, so this became 2u du is dx, and then when we rewrote the integral, we replaced dx with 2u du. The 2 came out. Oh, so what? It's not a 2?
No.
Okay, sorry.
Yeah, I was wondering where that.
That was, no. Okay. I was thinking about the previous problem. That's what it was. Right, the previous problem was 2. Thank you.
You saw that, right? I was like,
Thank you. You have to point those things out. And it's, you know what, it's actually a really good thing that you see that, because if you're sitting there and go, how the hell that happened, you either don't understand it or I made a mistake, right? So either way, you need to call it out. All right, that better? That better? Okay. I'm sitting here, I'm going, come on, Alexis. The 2, come on. What's that? Yeah, we'll fix it here. Thank you. Well, that's actually going to be nicer because the integration of that up is going to be easier, right? We don't have to scale it by a half. All right, well. All right, dw. We differentiate down is going to be du. And then v up, just e to the u. So this integral becomes 2. So this 2 right here is going to be passed through whatever I get now, right? Yes?
for V,
Uh-huh.
put 1 over U, e to the U, or no?
No. If it was like 2u, which it's not, I don't know where you get that crazy idea from. If this were 2u, then you would have to scale by 1/2.
Yeah.
But you don't scale by the variable. It's the coefficient of the variable. Think about that just for a second. If you put 1 over u,
Because the U would fall off when you take the derivative.
if you take the derivative, you're going to have to do like a product rule now.
Yeah.
And it's going to be nasty, and it's not that. So, okay. We good? So this 2 is going to distribute through to whatever this becomes. That's going to become the formula ultraviolet minus voodoo, even though we're not using those letters. So we said across the top is kind of like the ultraviolet. So U times e to the u would be first. minus integral and then the diagonal, right? Which is just e to the u du. And is this an integral that we can handle?
Yes.
Absolutely. So this is a good thing. So this becomes 2, let's see, u e to the u minus, what's the antiderivative of this?
E to the u.
E to the u. So just here, plus a constant, right? I'll do that at the end. In fact, I'll put it right here. I'll just put it right there. And now I'll pass the 2 through. 2u e to the u minus 2e to the u plus a constant. And I've had students ask me before, like, don't you have to multiply the 2 through, like, through the constant too? Like, shouldn't the constant have gone right here and the 2 multiplies through? It doesn't matter because 2 times a constant is still a constant. You don't know what that number is. It can be any number. So if I wrote 2c here, I wouldn't be wrong. But there's no reason to write 2c. And if I wrote negative c, it wouldn't be wrong either. It doesn't matter. Are we done? No, we have to go back to the original variable, which was x. So go root x. And so just replace all your u's with root x's. So this becomes 2 root x e to the root x minus 2e to the root x plus c. That should be the antiderivative. Questions? All right, I'd like to see if you can do one, all right, on your own. I mean, you can help each other out. But this is something that, remember from Cal 1, that if you had the natural log of x, right, the derivative of it was what? 1 over x. I wonder what its antiderivative is. So that's true, right? And we usually use absolute value plus c. That's true. So this is the relationship here, but that's not what I'm asking. So please see if you can figure this out. Help each other out, okay? If y'all can figure this out, I'll allow you to write this on your formula sheet. Okay, it'll be something you can keep on your formula sheet. But y'all have to figure it out. All right, go ahead. Enjoy. My hint to you is that it involves the technique in this section, which is called integration by parts. You're welcome. You have a question? Mm-hmm. Plus C.
Oh, yeah.
You're asking me if that's correct? You check. When you get your answer, you take its derivative, you should get natural log x, right? Works? You do product rule there?
Yeah.
Yep. Okay, good. That's it. That's correct.
It is?
Mm-hmm. So far. There's just one, right?
Oh, yeah, true.
You got the right table there. Just do your ultraviolet minus voodoo. That's right. This is what's x times 1 over x.
1x squared.
Nope. One of them is on top, one of them is on the bottom.
Oh, it's 1.
1. Okay, so anti. Okay, I'm just going to write the table up here. This is what you should have had. u was natural log x. dv should have been dx. Derivative of natural log x is 1 over x dx. V would then have to be the antiderivative, right, of 1, which is x, And then ultraviolet would be these two multiplied. I'll put the x in front of the natural log, minus integral. And then when you do v du, it's x times 1 over x dx. But x times 1 over x is just 1 dx. And the antiderivative of 1 is x. So x natural log x minus x, then plus a constant. That's it right there. You can check it. If you check it, you do a product rule on those, and things will start to go away, and you'll get natural log x. So you are free to write that down on your formulas. That's the only formula that I'm okay with you writing down, unless I tell you to write another one. All right. Be aware that on the test, right? If you come with your formula sheets, you can't have a bunch of your own stuff written all over them. It's not fair to anyone else. But that one you can have. All right. Well, we still have lots of time. Let's look at this last formula, or this last problem. Who has their book that has all the, anyone have the book that still has all the formulas in the back? I think yours does? Yours does too. Okay, you mind? It doesn't smell, I still smell a little like skunk on my hands. It's not that bad though anymore. If you still have all these formula sheets, there is actually a formula on reference page 9. It's formula number 73. And there's 120 formulas in this book. Here's what the formula says. I'll write it down here for you. It's negative 1 over n sine of n minus 1, or sine to the n minus 1 of u. I better switch this over to x's here. Cosine x plus n minus 1 over n integral sine to the n minus 2 x dx. Let me just double check that. Negative 1 over n sine n minus 1 x cosine x plus n minus 1. That's it. Okay. So this is a formula in the book, and this is what we call a reduction formula. And let's try and appreciate what's happening here. Okay. Let's say I'm trying to find the antiderivative of sine cubed x dx. That will be very difficult to do, all right, with any technique that we have right now. Because, well, do you see the inherent problems with this? Like, what are you going to choose to let be your u and your dv? It's going to be a difficult choice. Now, you are allowed, you could split it up. You could write as sine squared x times sine x dx, and you could choose maybe that to be your u and this to be your dv. Okay? But it's going to be a mess. According to this formula, we don't have to do any of that. All we have to do is identify what n is, which for us would be what? 3, and then plug into this formula. So it'll be, for us, negative 1 over 3 sine raised to the n minus 1. So sine squared x cosine x plus n minus 1. 2 over n, which is 3, integral of sine to the n minus 2. So what's n minus 2? Sine x dx. Do you know the antiderivative of sine? Negative cosine, right? So this just becomes negative 1/3 sine squared x cosine x plus, actually it's going to be minus, won't it?
Yes.
Because I'll pull the negative out. Negative 2/3 cosine x plus c. And that would be the answer, wouldn't it? Yeah, if you don't have the formula, then you would have to do it more rigorously. Which the next section involves how we handle powers, basically trig integrals. Integrals that have trig functions in them. So we will do this the harder way next class. Or next time, well, next time we'll review, right? Well, we're not going to review for the whole day. We don't have enough time in this class for that. So we'll probably get into this next class, but it won't be on the test per se. Check my schedule. How far does this schedule say we go? Integration by parts.
Today's the last day.
It says review, and we won't spend an hour 40 minutes reviewing. All right, this isn't Math 305 or anything like that. We don't spend 2 hours reviewing for a test in here. Sorry. But I wanted to give us a little bit of time. Well, it is more reviewing, but just not here. It's not happening in class. It's happening on your own. So, all right. So the usefulness of this formula would be that let's say that this power was, let's say, 7. Then things would change here, right? This would become 7, then this would become 6, and then this would become 6/7, and then this one would become 5. And then you're like, crap, well, I don't know how to do that.
You gotta do it again.
So what you do is say, but this part, this is your new universe, right? I do that formula again. And when I do that formula again, what integral will be popping out at the very end of it?
3.
Sine cubed. And then you do it again. But it's just fill in, right? Like you're never actually integrating anything. Look, no, it's reducing the power every time, isn't it? It's going from sine to the n down to the n minus 2. So if you do it one time, it's going to reduce the power by 2. If you do it a second time, it'll reduce the original one by 4 total. And you can do that, and you can take it all the way down to either sine or sine to the first power or sine squared. Those are the two different things that you could wind up with at the end. Sine to the first power is easy. Sine squared, well, we can do that next class. All right? That turns out to be easy also. So do you see sort of the value of this sort of formula to have it? Yes? Where does it come from? So that's what I'm going to show you where the formula comes from. All right? You have homework problem. You have, I think, at least one homework problem where you're asked to come up with a reduction formula. So this isn't totally out of the realm of feasible, reasonable questions to ask a student. Maybe not on a test, maybe as a bonus. But it's still something that you shouldn't look at that and be like, oh, man, no way. You know, this is doable, all right? I'll give you a big hint on how to start this. This is ultraviolet minus voodoo, believe it or not. That's ultraviolet minus voodoo. So if that's ultraviolet minus voodoo, then this has to be ultraviolet, right? Which means one of those is U, and one of those is V. Right? So let's see here. What do you think? This is U, and this is dV. So you're choosing out of this one a U and a dV, right? Any ideas? Okay, U is sine to the n minus 1 of x. But I don't see that there. I mean, I do, but I'm trying to help everyone see it. Where is that here?
It's the first part of the equation.
Is x to the n the same as x to the n minus 1 times x to the first power? Is that the same thing? If you have the same base, what do you do to the exponents? You add them, right? Add these up. What happens when you do n minus 1 plus 1? You get n, right? So this is the same as this? What I want everyone to see here is that we could have rewritten this integral as sine to the n minus 1 of x times sine x dx. Couldn't we have? Now that's not a natural move to do that, but we could do it, couldn't we? If we do that, then you would choose your u to be sine to the n minus 1x. And that forces your dv to be what? Sine x dx. You follow that? And now let's go and write out everything that would happen now. So we're going to try and get to this formula at the end. Let's see if we can. What's the antiderivative of sine? Negative cosine x. And then very carefully here, what is the derivative of sine to a power? So I'll remind you, like if you had sine to the fourth x here, and I said take the derivative, the first thing you would do is what? You bring the 4 out and then subtract 1 from the power, wouldn't you? And then you take derivative of the sine, which would give you cosine, right? So over here, we're going to drop what out front? N minus 1. And then it'll be sine to what power? Take 1 away, so n minus 2 of x, you see that? Times the derivative of sine, which is cosine, and then dx. I ran out of room. But do you see I'm starting to get pieces in here that it's kind of promising? Questions? All right. I want to leave that formula up here because I want to be able at the very end to go back and say, look, we got it, okay? So I'm going to say from here, what we have so far is ultraviolet minus voodoo. So let's do ultraviolet. It'll be this, right, times this. So that's negative sine to the n minus 1 x cosine x. That kind of looks like this, doesn't it? I have the negative. I have sine the n minus 1x. I have cosine x. I just don't have 1 over n. It's okay. It's all right. At least I feel good about it, right? It looks kind of the same. Then, according to the formula, minus integral voodoo. So this times this. What are the constants? Are there any constants? Negative, right? Negative 1 and n minus 1. So I can pull out a negative n minus 1, can't I? I'm going to put that in front of the integral. When I pull the negative out, it's actually become what? Plus and n minus 1. Integral. And then all the other stuff. So what? Sine to the n minus 2x times cosine times cosine. Cosine squared? Times dx. The negative I already pulled out. This negative came with this and came out of the integral, and that's what made this a plus. Do you all have any questions on this? We're not done, right? Does this look like this? Kind of, but I've got this cosine squared, this one doesn't, and so I don't know. Now I'm starting to get a little concerned. Nope, nope. Watch. This equals negative sine to the n minus 1 x cosine x plus n minus 1 integral sine to the n minus